here. I was here when I think Calvin Moore was having a hard hat and was supervising the digging for this institute. So it's a great pleasure to be back. I would like to speak today about a problem which arose as a challenge from our nuclear physicist colleagues in France. So Jean-Bernard Zibert, about 10 years ago, started to put up the problem of looking for the higher analogs of the Coxeter graphs. So Coxeter graphs are somehow related to SU2. So what would be the higher graphs? And what came out was a lot of structure, and actually he helped it a little bit. So in the spirit of these days, I think when private foundations put a lot of money into mathematics, he put some of his own. So he put one bottle of champagne for the SU3 problem, 2 bottles for SU4, I think 3 for SU5, and so that he wouldn't be completely bankrupted, he stopped there. So stopped at a total of half a case. So he gave out up to now. This is a 1 bottle and almost a 2 bottle now. Now, what is the problem? So we start with that. The problem can be phrased as usual. As you have seen here, there are a lot of equivalent languages, and I'll come to this later. You can rephrase any problem with a minimum of effort. You can take it in intertwiners, topological quantum field theory, if you like that, or you can make it into type 3 factors, or into category theory or so. So it's just like a dictionary. But the main problem remains the same. You have to solve the problem in one of these forms and then put it in the other. So here's how the problem starts. You see, these are the SU. Well, first I should maybe put on the plan of my talk. This was just a teaser, I think. So the Coxeter graphs are not necessarily affine Coxeter graphs, are Mackay graphs. So they are tensor graphs for some quantum subgroups, for subgroups of SU2 or respectively quantum subgroups of SU2. So there are some mathematical objects which have irreducible representations at the vertices of any Coxeter graph. This is the first part. Then I'd like to describe how how one uses modular invariance to treat these graphs and to access the higher graphs. And then in the final part, I'm going to switch course in a way, and there's an application of these, show that 2 very familiar concepts which have been around for about 110 years now, started by Felix Klein, the study of subgroups of SU2, and the one started by his student Sophus Lee, the simple Lie groups. So these 2 branches of math have evolved, one into Hilbert's invariant theory, the other into the study of Lie groups in general and higher dimensional things. They have been almost unconnected. There was a very feeble bridge by means of singularity theory, which wouldn't work anyway in higher dimensions because groups like SU3 and SU4 just don't have enough symmetric representations. So most of their representations are on tensors. So that bridge wouldn't work. So I'd like to establish a bridge now between the 2 and show that in the final part that simple Lie groups exist because SU2 has subgroups. So the subgroups, the fact that you can squeeze inside SU2 a subgroup gives you exactly the information on how to assemble some copies of SU2 and make a simple Lie group. And this won't be just an exercise in known things, so this carries over to the new subgroups of SU3, SU4, and so on. So these have a geometry. They have a root system and a weight system, a root set and a weight system, which is new. So here are the Coxeter graphs. They're well known, and I think they Coxeter Dynkin diagrams. I met Dynkin. He just came to Penn State a couple of months ago. He was about 19 when Gelfand gave him as an exercise to present the new theory of root systems and to organize it a little bit, which he did. So these are the Dynkin diagrams. These are the not so well-known diagrams, which also have norm less than 2. So these are all the small graphs. You know, they are small numbers, 1, 2, 3, and so on. And they are small graphs, graphs of small norm. And this is a list. And these are the tadpoles. And for a reason which would come up exactly the cells that I'm going to talk about later, these do not appear in connection with SU2. So SU2 has nothing to do with these graphs. There's a cohomological obstruction. These are the affine graphs, and the way they appear as symmetries. I think this is fairly well known now. You take some subgroup like the symmetries of the icosahedron. It's the alternating group on the 5 cubes. You see here a cube. These are the irreducibles, the 5 irreducibles of the alternating group. When you lift it to SU2, you get these 9 representations. And if you draw the graph of tensoring with a 2-dimensional, it's a subgroup of SU2, you get a graph of norm 2. And this is the affine E8 graph, which you see here. So this is what's called the Mackay correspondence. For some reason, people who did representation theory were extremely reluctant for the first 100 years to tensor them. So Mackay in the 1990s finally started to tensor them and noticed that they have this wonderful structure. And this is in a way what we are doing in a different way with bimodules, for instance, and so on in operator algebra. So it's the same kind of general method. So this way you get, of course, only the graphs of norm 2. Now the previous graphs, the ADE graphs, have norms slightly less than 2, 2 cosine of pi over n, where n is a Coxeter number. So there must be some representation of dimension 2 cosine of pi over n, which they are representing. Now, just to illustrate a bit how you do a cutoff, you see this is the way we count usually for the irreducibles of SU2. Is a trivial, the 2-dimensional and so on, the dimension you see grows linearly. If you want to count non-linearly with a cutoff, your quantum number, instead of being n, is sine of n plus 1 pi over some number n divided by sine of pi over n. And this is how the numbers look like. You see, it still starts with 1, and then they drop back. So in particular, in this case, the 5th representation is killed. It has dimension 0. Yes? And the 6th one should be counted as minus, as negative the 4th one. That's a proper way to do it. Just take a negative copy of that. So that's a quantum way of counting, and that's how you have cutoff. And this ingredient had been around for another 150 years. People did basic hypergeometric series with a Q in them. And it took, again, a very long time till people realized that groups should be also cut exactly the same way. So this was Drinfeld's and Jimbo's point of view. So if you cut this way SU2, it's going to have subgroups. So this quantum SU2, so you see here the cutoff SU2, it's going to have subgroups, and this is what we're going to talk about. Here's how you cut SU3. Instead of having the weights in a triangle, they stop. I mean, in an infinite cone, you have the representations in a triangle, and these on the board are 0. So this is a cutoff SU3 at some root of unity. It's just tripartite naturally. So the representations of SU3, just like the SU2, are bipartite. These are tripartite. Right. It's the action of the center. And you have here something else which appears only in this case. This one is one-dimensional. Now these corners are also one-dimensional. And they form the group Z mod 3. And this group Z mod 3 is a center which appears in Lie groups. So this is one of the very feeble bridges between the two theories. So it's multiplicative characters, and it will be very prominent in what follows. Now, what was Hubert's problem? The higher graphs, and he put some conditions on this by analogy with SU2. He asked first that the graph be tripartite. This was at first this was a mistake in a way, because the SU2 graphs are not bipartite. They are the affine graphs, which are the affine ANs are n-gons, so n can be odd. So the true condition is that the SU2 graphs have no tadpoles, and so this one was removed last summer by Hubert and Petkova. Then there should be some involution. He asked on the vertices coming from conjugation. So in sigma, the generator of SU3 has the irreducible has a conjugate. The graph matrix is normal because you have braiding between representations. So when you tensor A tensor B, decomposes the same way as B tensor A. And then it should have the graph should have the same Perron-Frobenius eigenvalue as SU3. So if you take the graph E8, for instance, it has Perron-Frobenius eigenvalue 2 cosine of pi over 30. That's exactly the same as one of the graphs AN, A29. Moreover, all its eigenvalues are among the eigenvalues of the graph A29. So this eigenvalue set is called the exponents of the graph in Lie groups. So if you take full spectrum, and the ultimate goal is to have an action of the Hecke algebra of SU3. Now, this was drawn, as I said, by analogy with SU2, and unfortunately, that's not the way we deal with the SU2 graphs. The SU2 graphs are simply the graphs which have small norm with no other condition other than the tadpole. So there should be a local condition, something that you can check on the graph, which should determine whether the graph belongs to SU3 or not. So, for instance, somebody gives you a graph, and you want to know whether it's a graph of irreducible representations of a subgroup of the usual SU3. There should be a condition that you check on that graph, and if that condition is checked, so there should be a group. So it should be a bit in the spirit of what Professor Doplicher was saying the other day. So a condition which should give you simply the existence of a group. And this condition is local here. It's in the same spirit. So we replace these conditions by yes.
What does this Hecke algebra action correspond to?
Oh, this is just the fact that you should get some Young-Baxter equation solutions, and I'm going to come to that. That's what they wanted. The physicists always love that because they can make a statistical mechanical model.
Right, but you mean the Hecke algebra of SU3?
Yes, of SU3 exactly. So now of SU3. So you see. Yeah, it's they just wanted the Young-Baxter representation, and this would come out in yes, I think they were just calling it the Hecke algebra, but so this would come out in a minute. So actually, the good way to look at it turned out to be different. So the problem had to be rephrased. Fortunately, Hubert didn't change his mind on the bottles for that. the problem as it was set had some solutions which had no connection whatsoever with SU3 or SU4 and so on. So it needed to be rephrased first. It turns out that, okay, the data consists of vertices, edges, and cells. So there are some numbers in the triangles which appear. So there are some numbers on the graph. That's the only extra data that appears in the SU3. Some numbers which live in the triangles of the graph. And these numbers should satisfy some local condition, just something involving the neighbors. Once you have those conditions, everything else follows. So all these properties follow. And in particular, you get all the data to get 6J symbols, to get to explain the shape of the graphs, to get these Young-Baxter solutions and so forth. Now, just to explain the context a bit, I will start with a baby model. So this is a baby model of a maximal, I will call the maximal atlas. So this baby model is Morita theory. You have some numbers, 1, 2, 3. The elements of type 2, 3 are the matrices 2 by 3. Yes, it's clear that you can tensor 1, 2 with a 2, 3 and get a 1, 3, right? And if we want a numerical invariant for the vertex, so what's this 3 here? That's a trace of the identity. So this is a label for the vertex. So this is a baby model. It's in, if we would work with three-dimensional topological quantum field theory, for instance, which is one of these equivalent languages, this would be one dimension lower. This would be two-dimensional TQFT. Now, if you want to go to higher things, let's look a bit at the finite or compact groups in the same spirit. If you have some vertices now, just like the 1, 2, 3 before, which consists of a pair. So your data is a finite group here, finite group G, and the vertices are labeled by a subgroup H of G, together with a scalar 2 cocycle, which is it's called a Schur multiplier. It characterizes a class of projective representations. And an element of type HK is basically a double coset HGK and an irreducible of the stabilizer H intersected with GKG inverse, and of course perturbed by the 2 cocycles. So it's a projective representation.
So the cocycle is a cocycle of H or of G?
Well, you have one of, no, it's a cocycle on H. And here you have a cocycle on K. You bring them together, and they give you a projective representation of this. So they give you a cocycle which gives you projective representation. So this is a model. So it shows that this is what we should have in mind when we speak about this maximal atlas. I mean, when we start with something like group elements and we want to know what are all the bimodules that we can make which relate to this. So you see, all the bimodules come from subgroups. So that's why we should think about the graphs of Zubair, not only think about them, but deal with them. They are really subgroups of quantum SU3. So there's that quantum SU3, SU4, or any other thing like this that you have seen, and that one has subgroups. And what we're dealing with are the irreducibles of these subgroups, just like in this picture. So this is a classical picture of the subgroups. So let me show you the analogous picture for the subgroups of SU2. This is, so this has been, it has appeared about a year ago in print. It's the Lectures in Operator Theory of the Fields Institute. I think it's appearing in a different language right now in different places, but it's, so what you can, what you have here is the maximal atlas. If you take the quantum SU2 in this particular case, at the 12th root of unity. So this representation, where my stick is, this representation should have dimension 12. And because the quantum number 12 is 0 now, it doesn't exist anymore. So it's cut off. So this is just like SU2 at the root of unity. And we're trying to find its subgroup. And we find that indeed there are 3 vertices labeled with D and E. So this is just like the binary dihedral group. And this is just like the binary tetrahedral group, D6. And as you see here, these are the bimodules, if you like it, bimodule picture of type AD. They form exactly the graph D. The bimodules of type AE form exactly the graph E6. And the bimodules of type DD form this picture here. And the bimodules of type EE form, there are these 12 elements right here. And your invariant, instead of being that number n, the trace of the identity, is now what's called a modular invariant. So it's a matrix with non-negative entries. And moreover, exactly like the matrices of type 3-3 are the product, the tensor product of three-dimensional vectors with three-dimensional vectors, here these 12 elements are the tensor product of the left chiral graph, which is this red graph, with the right chiral graph, tensored over the ambichirals here, over the intersection. And this gives all the structure. So now I'd like to talk very fast about the cells. So these cells which appear here on the graph. So this is a graph for a quantum subgroup of SU3. See it here, it's this. There are 12 irreducibles. And the graph is a graph of tensoring with a generator. So if you take this particular irreducible K, and you tensor it with a generator, you get J, and you get all the arrows that come out of it. Now, you have a lot of triangles here. You see, this is built of triangles, just like the irreducibles of SU3. And in each triangle, you have a number. Now, this number, if you do topological quantum field theory, is a picture of this kind, if you do diagrams in the plane and so. Oh no, these are the irreducibles of a subgroup of quantum SU3. Yes, so it's a subgroup which has 12 irreducibles. This particular one has a classical counterpart which has about 16 irreducibles or so. Or the group of order, I think 27 or something. But this is a quantum group. And the cells are the following. And what lives in the triangle, you see? What you do is you compose the edges here. So you start from I, you see we have this IJK, yes? You start from I, which is an irreducible, you tensor it with, this is a generator of SU3. You know that the generator to the third power contains the trivial representation. And then you go around the triangle and you end up back to the irreducible I. So since I is an irreducible, you get a number. And this is a number that lives in the cell, in the triangle. And these are the numbers which are axiomatized. They depend on the choice of intertwiner. So there's a gauge. You can multiply any intertwiner by a scalar. If you have 2 with U2 and so. Up to that gauge, it's uniquely determined. And these are now, so these numbers in the cells must satisfy, as I was saying, a cohomological condition. It's a which is basically that if you have a frame which is a pair of edges in the graph or a bigger frame here, see, this bigger opening, if you make all the pockets, see this is very cohomological here, if you make all these pockets which have as boundary the given frame, and you take the product of the cells, and then you sum, you should get Kronecker symbol. So these are the local conditions. So if you find these numbers in the triangles which satisfy these equations, then you know that you have the irreducibles of a subgroup of SU3, of quantum SU3. So now we have the method to check whether a graph is good or not. And one of the graphs which was in, Zuber put all kinds of filters on these graphs, but still there was a fake one which remained. It escaped all detection, and it remained in the list, so which could be cleared out by the cells. Now with these cells, once you have these cells, so here I should answer the question which was just asked a minute ago. What do we do with them? For instance, we can do these statistic solvable models. So from each of these, we can take the cells. You see, the cells are numbers in the triangles. So we can take this crossing. This braiding is well known for SU3. Now we make this out of two triangles. See, we divide the square into two triangles. We have the numbers in the cells. We use some root of unity here. And we get some elements which satisfy the Young-Baxter relation. So out of each of these graphs, you can get a solution of the Young-Baxter equations, which was one of the ultimate goals of the physicists, and they're using it. Now they're computing these explicitly for each model and so on. Now, from our point of view, if you have cells, then you can compute any kind of graph with a boundary. So the upper graph is computed by simply dividing it into little triangles, as you see here. So it means that once you have these cells, you can do the full computation. And such cells, a bit more degenerate, exist also for SU2, and they prevent exactly the tadpoles. So it's a cell obstruction. Sorry? So in the middle, these are AA bimodules. They are the reducibles of quantum SU3, or imagine, yes, so in this particular case. And these are AE bimodules, which are the vertices of our graph. So this could be the graph E8, for instance. These would be the elements of E8, yes? And here, this is the most general diagram the most general planar diagram, if you want, which you can compute. It has AA things in the middle, and it has AE things at the boundary. Once you compute these by diagonalization, you can get all the EE bimodules, so you can get everything you want about it. So the only consistency relation is the consistency between cells. So once you know the cells, you can compute the whole model. All the data is there.
So this is just an example?
Yeah, you can compute any diagram of this kind using the triangles. Yes, you can set using this formula. You can cut it into little pieces and just concentrate on the nodes. And there are cells like this also for SU4, for any of the groups. You have also triangular cells. So it means that from the point of view of planar diagrams, the model is done once you have the cells. Now, I should mention one or two more things about the modular invariance. Well, the theory of modular invariance was done, I think, in quite a bit of detail. I think it's now done and published, but I should like instead to concentrate a bit on the what I call the modular splitting. So here's the argument in the opposite direction. Now the cells tell you whether the graph is good, but how do you compute on all the graphs? So how do you make an exhaustive list? The starting points are modular invariants. So, and there's a principle which is there's a key technique. So I'm going to put it out here, so it can be translated into any of these 10 languages or so which are around at this conference without any effort. And the main point is that it has not appeared before in any of these languages. Might happen from now on. So here's first the modular theory. You see you have a Hilbert space associated to the torus. The automorphisms, the basis of this torus space is called chi-i, chi-j bar. And the automorphisms are the modular group. Just automorphisms of the torus. Now how do you get a special vector in it? If you want, for instance, a graph, let's say, a graph of type EE, so some invariant for one of these vertices, E, in our something like an invariant for this vertex E. Okay, it's called here B in what follows. We have AA vertices and we want a vertex B. What we do is fill the torus in a modular invariant way. You see, if you fill it like a bagel, then when you do the S transformation, the filling spills out. But if you fill it like a cone, which is not a manifold, so you just take the cone over it, this gives you a modular invariant filling. Whatever you do to the surface happens to the cone. So that is going to give you and since it has a funny vertex, this vertex B, this vertex cannot be changed by the usual moves, changes of triangulation. So it gives you an invariant of the vertex B. And so it gives you this form, sum of Mij, chi-i, chi-j. This is a vector. And the Mij's are actual dimensions. They're dimensions of this lid space, of the disk with a puncture B. And these are the modular invariant coefficients. And here's the absolute key lemma. So I should, well, I don't know whether I didn't know whether to put it out or not, but anyway, so this is, it will appear in the proceedings of the Bariloche conference where this was first presented. But key thing is this equality. You take the cylinder with one point, with one puncture, and you cut it in two different ways. You see, if it's cut like this, it's cut into a trouser surface and a lid. So what you read here, on the trouser surface, you have usual fusion numbers, n, x, x prime, x double prime, and so on. These are just your basic little Richardson coefficients, which are well known. And here you have the modular invariant. That's a lid. So the left member is something that you compute out of the modular invariant. On the right-hand side, you see the same picture but re-triangulated. You triangulate it with an edge like this. And you see now you have the edges of type BB here. So this sum splits into a sum of two terms, the sum of all edges V of type BB, of some matrix which is a modular semi-invariant, I call it. This is a modular semi-invariant for the, this is how you get the modular semi-invariant for the SU, for the, E6. This is a modular invariant matrix, and these are its neighbors. So you have some matrix of this kind at every vertex. So this is a data which is contained in the graph between the graph of the asymptotic inclusion. So this is exactly the lower graph of the asymptotic inclusion. So that way we get the asymptotic inclusion directly out of the modular invariant. It's just like reconstructing a big beast out of a single tooth. And so just one line of the modular invariant is enough to build one of these graphs with a program. So this is a modular splitting principle, and it goes into algorithms and so on. It also gives level bounds. Now, if you heard Terry Gannon, who's doing modular invariants, speak about these, well, he starts a list of modular invariants and then goes up to level, I think, 10,000 these days with a desk computer, no problem. The problem is that he finds nothing above level about 8 or so. So there are no exceptionals except at the first level. So after you cut off, if you cut off too far, the SU3 or SU4 and so on, you don't find any more exceptionals. E8, the graph E8 happens at level 28, is Coxeter number 30. There's no exceptional after that. So there's a general theorem which comes out of the modular splitting, which tells you that there's no exceptional after a certain level. And the fundamental inequality is this. You have the clearing. The clearing is the level up to the first modular invariant, so up to half of the first modular invariant. So if you remember the graph E8, it starts with 5 straight lines. The first modular invariant there happens at level 10. It's chi0 plus chi10. So this half, this clearing, for the duration of this clearing, the graph of the E8 looks exactly like the graph AN. So there's no invariant whatsoever for a while. And this is this clearing. And what this tells you is that if you take the fusion, if you take the little Richardson fusion, M times its conjugate, this is the first non-trivial modular invariant, M times its conjugate, and you take only the things which are in the clearing out of this. So you take the product, the fusion, and you take only the part that's in the clearing. This is going to have mass less than M. Now look, this is M times M, so this is M square. So constant times M square is less than M in mass. So this shows that the gap cannot be too big. So for SU2, you get it this way on the nose, that there's no gap bigger than 10, which is the one that happens in E8. Either that or the mass of M must be 1. Now, if the mass of M is 1, then you are at one of those corners of the triangle, and that gives you orbifolds. If the modular invariant is concentrated on the corner, you remember that was the group Z3 for SU3, Z4 for SU4. So you can have SU4 divided by 2, SU4 divided by 4, and so on. Those are the series, just like the series Dn. Those exist, of course, at high levels. But in order to have an exceptional, the gap cannot be too big. On the other hand, however, there's an obstruction because of the T matrix. The T matrix, which consists of twisting the torus, should have enough time to make one full round in order to get a modular invariant. It should go once around the clock. And that cannot happen if you move too slowly in this gap. So if you are at very high level, there's no time for T to reach back the identity. So this gives you the bound on the level. And this is the fundamental inequality. It takes some work to get out of this an actual bound, but anyway, you get a very manageable bound in any case. So now the other thing about the list that I'm going to put out are the proof of flatness, which I'd like to put up now. So this is It's a new proof of flatness, but the ingredients are all in the lectures at the Fields Institute 6 years ago. It gives you flatness without any effort for any graph related to SU2, SU3, and so on. So here's how it goes. It's called the bootstrap approach. So what bootstrap means is that you lift yourself, I have no shoelaces. Yes, no lifting anyone else by the doesn't count. So you need to lift yourself by the shoelaces. This is what physicists call the bootstrap approach. And so it takes a bit of exercise, I think, to do that. But this is what we do here. So you see, we have the graph. This is a graph of E6, as you recognize. There's a left part, a right part, and the product over the ambichirals. And there's an ambichiral twist sometimes, which tells you how the two are assembled. And if you have this data, that's the only observation, that if you have this data, then this determines the graph E6. So I'm going to go very fast through how you prove what happens, for instance, for SU2 at level 16, so Coxeter number 18. The possible graphs are A15, D10, E7. A15, the flat part must be A15. The only ambicirals by a mass argument must be the whole A15. The only possible twist because of modular constraints is the identity. Conclusion, A15 is flat, and this is the important one. No other graph can have flat part A15. So A15 produces only A15 by this argument. So you know that E7 cannot have flat part A15. Now there you take D10, possible flat part, A15, but this one is taken by the first argument, so what left is D10. So D10 is flat. The ambichiral part, D10 even. It has as twist the identity and a weird twist, which appears only at this level. The identity produces itself. But with this twist, it produces one more graph. We don't even need to look anymore at E7. We know E7 is a graph. We know that D10 produces a graph, so that must be E7. Conclusion, E7 is not flat. Its flat part must be D10. I mean, these took a lot of work. So similarly, you can prove that E6, E8 are flat and so on. So the problem was not so much the subgroups of SU2, but if you got to the monsters of SU3 or SU4, any kind of computation would have blown up the whole computer. So that's a level 16. The Coxeter number is a level plus a rank, so it's a level plus a dual Coxeter number. So it's 16 plus 2, which is 18. Oh yes, it's an error. Sorry, it's A17. So thank you very much, Dietmar. So it's A17 there, all over. Yes. Okay. So here I have a folder called Zoology, the zoo. So these are some of the beasts. I have just a few minutes for this, and then so these are the subgroups and modules of SU2 and SU3. Okay, you see them here. This is the SU2, the series A and D. Some of them are only modules; they don't have self-fusion. E7, as you saw before, the subfactor doesn't exist. You cannot tensor these and get another vertex of SU3. So some of them are just like modules, just like cosets. Some others are like subgroups, so you can tensor them with themselves. So these are always bold in these pictures. So E6 and D8 are flat. For SU3, here are the series. This is the AN series, which you recognize. This is the cut of SU3. This is an orbifold. You cut this in 3, and you glue it, and this is exactly 1/3 of SU3, of the triangle. This looks like a pita pocket here. There are some conjugate orbifold series which come from the fact that SU3 as a Lie group is built on the graph A2. A2 has a symmetry. So this gives you a symmetry of the modular invariant. And it gives you some strange, you see, this is a conjugate of this, although you wouldn't notice it on, the graphs don't look the same. And you see this one is one which was not tripartite. So this one was thrown away first by Zuber then it was put back. This is a threefold cover of this. You see every point becomes a triangle here. And this is made of octahedra, yes, all this structure. And then there are the 7 exceptionals. 3 of them flat subgroups, and the others different quotients, different modules of these flat things. And this is everything that happens with SU3. So this is a complete list, and this was one about. Now for the other one, for SU4, I still have to compute the cells on one of the graphs. It's mild by the standards of the business. I mean, there are 16,000, 1,600 nonlinear equations which are satisfied by the cells, but they're local. So you have to keep track of 50 degrees of freedom. Yeah, it's not so bad. I mean, it takes about 1 day or so for a graph. So you can put 1 day. There are very few graphs. This is the biggest surprise. There are so few of them, and they get fewer as you go higher. So you'd expect SU4 to have more exceptionals than SU3, and so on, but it doesn't happen. So this is what happens for SU4. So the first one is questionable. This one is not yet so clear, but these are the series. You recognize here SU4, yes, made of tetrahedra. This is 1/2 of that, A4/2. I didn't call it D because I prefer to just divide it by 2. And this is a quotient by 4. Amazingly, the quotient by 4 exists only for 2, 6, and 8 modulo 8. So it doesn't exist for the others. There's no A4/4 for modular reasons and for cell reasons. So the cells just don't exist on some of these terms. And now these are the conjugate ones. You see they're made of, they have this strange, these had to be guessed. There was no method to do them at all. And this was a trickier one to guess. This one also exists because of the cells only at 2, 6, 8 modulo 8. And then there are 6 exceptionals, fewer than for SU3. This one is the one which I'm still working on, but the others are all determined. This one was first put up by Zuber. This orbifold by Evans and Kawahigashi. And this is new, and it's a first example of a truly exotic subgroup. It doesn't come from any conformal inclusion or anything like this. There was a long-standing conjecture, I think you saw it even on one of the slides in this conference, that that everything was produced by conformal inclusions. Well, this one is not. And this is its module. So, yes, so let me just magnify it. And this is the analog of the graph E7. So this is the analog of the graph E7. This is monster and its module. If you look carefully in the middle of the module of the monster, well, it's a quantum monster. The monster is taken. But you see, here it's not symmetric. There's a subtle Möbius band in the middle of it, which had to be detected with spectral techniques, the shape of the graph. See here, if you follow what happens with the red edges, which is not so easy, you find the Möbius band in it. And this is the spectrum. This is how you compute the spectrum. So the spectrum with the modular theory, which was developed in Canada. And I won't put, these are the twists, some of the twists which give rise to bimodule. So you see, this is how the twists, the groups are always E mod n or something, and so it's very easy to compute what are all the twists. And each twist gives rise to a module. So this twist gives rise to this module, this to this module, and so forth. What do we do with these things? So they are subgroups. Do they have something? And this is the third part, and maybe the most surprising part of what I'll be talking about. It will be short. It's just a half-line formula, but it geometrizes all these constructions. So behind each of these, there's a root system, a new type of root system, and the weight graph. So here's how we multiply. Here's the table of multiplication. The people in operator algebras know this very well. I just put it here. For reference, this is AN, you see SU2 at level 6, times D5 gives you D5. So this is tensoring table. These are the numbers. And these numbers satisfy, if you notice, the sum of these three, 1 plus 1 plus 1, is the sum of these two, 2 plus 1. So you compute them just like the numbers just like the usual table that you do in grade school for the binomial coefficients. Now, this is the theorem. You have a simple Lie group of rank R. So the usual example is SU2. And you just take a product. I should put a picture of this product here. So you see here we have the Cartesian product between the graph D5 here, which is a subgroup of quantum SU2, and here's the weight lattice of SU2, just a piece of length 16 of that. And you take the Cartesian product, you take the graded product, even with even and odd with odd. And you have these points, these dots in the Cartesian product. So they're just products of representations. And what I am saying is that these are the roots of the Lie group of type D5. All of them at once, with no particular distinguished simple roots. So just like in Lustig's canonical basis. And the inner product is given by this simple formula. The inner product of a pair AX with a pair BY is the sum over the Weyl group of the sign epsilon of W times the fusion number B minus A plus W, that's a Weyl element, times the rho, which is the Weyl vector. You remember it appears in the Weyl formula. W rho minus rho, X to Y. So what happens here is an observation which should have been done by us long time ago, is simply that if you look at these numbers here, then if you look at one number and if you look at the number 2 floors up, they differ by at most 1. And in a very strange way, there's no easy proof for this. So they differ by +1 or -1 or 0. This is exactly the inner product in the root lattice. So this was the observation which gave rise to this. But this formula applies not only to give us the usual root systems, I mean the root systems that we all know, root systems on which Lie's theory is based. If we plug here instead a subgroup of SU3 or of quantum SU3, of quantum SU4 or of anything like this, then, see, this is how the Cartesian product would look like. See, you should compare it with that. Oh, it looks a bit more complicated. So you see, it's simply the Cartesian product between, so here's the usual D4 for comparison. The graph D4 times the weight lattice of SU2. That's on the side. So here you have exactly the roots of the usual Lie group of type D4. Now here you have a more exotic one. You have a subgroup of quantum SU3 that you saw in the pictures before. And this is, of course, the weight space of SU3. So you take the graded Cartesian product. You notice that in each of these little things, I should magnify them a bit now. I'm coming from Japan where these projectors are always one step ahead, so they had a zoom. But here we have to do the zoom by ourselves. We learn new tricks there. So this is how it looks zoomed out, yes? And so these are roots. There are 256 roots, Each of them has, this is the inner product, this is a table of the inner product with this particular root. So the root with the inner product with itself, instead of being as usual, the inner product is 2, right, for the usual Lie groups. Here the inner product is the order of the Weil group, so that 2 in this natural construction appears to be exactly the Weil group of SU2. So if you use SU3, then you have vectors of length square root of 6. And all the inner products are going to be 0, which is marked here as a dot, so that you see the patterns better. And 2 minus 2 and 1 minus 1 and so on. So they have a very strange geometry. And the proof of this, which is, so this is the last slide that I wanted to put. The proof of this is based on the fact that, you see, what I gave you was this, what we had here was just a Cartesian product, pairs between vertices of the graph and, irreducibles of the subgroup and irreducibles of the whole group, SU3 and its subgroup. Now, this big matrix of inner products, why is it positively defined? It's positively defined because it's a projection matrix, so it's an idempotent. I don't think this has been observed even for the usual root lattices. So what I'm saying here is that if you make a big matrix in a root system with all the inner product between any two roots, not just a Cartan matrix for the simple roots, you take all the roots and you make a big matrix. That matrix is a projection up to a scalar. It's a projection onto the weight lattice. That's where these roots live. So there are many roots, but they are in a small space. So it's a projection on that space. So here you can check immediately with fusion that this formula gives you an idempotent. Once you have the idempotent, it means that it's positively defined. And where does it project? It projects exactly on the functions which have the property that I mentioned here, that the sum of neighbors. You see, we have a pair between an irreducible of SU2 and an irreducible of the subgroup. So we can take sum of neighbors of the Laplacian in this direction, in the horizontal direction, 1 plus 1 plus 1, and the sum of neighbors in the vertical direction, 2 plus 1, and they must be the same. These I call harmonic functions. Yes, delta G minus delta S of F is 0, and they are the root, the weight system. So all the integer valued functions with this property are the weights. So what we have now is a new geometry for each of these things that you saw. There's a new and strange geometry in which you have a weight lattice, which is just the usual lattice, and you have in it some unimodular vectors of length root 6 for SU3, root and so on, root 24 for SU4, and which have a strange geometry. So I didn't, okay, so I think I should stop here.
Stopping on time.
I thought I was 10 minutes late. Yeah.
So the local thing that you have for quantum SU3,
right.
You try to do it for usual SU3.
Exactly.
Does it work?
Yes, and it gives you, so exactly, it gives you, let me show you one in which I have actually computed by hand. There's a subgroup of SU3. I think it's related to the name of Klein also. Is there some chocks? Oh yeah, here. Which has two representations of dimension 3. So this is a 3-dimensional. This is another 3-dimensional. And then it has 9 one-dimensionals. So it's a bit like the quaternion group. Yes, so all of these go like this, yes. So this would be the quaternion group. It's a 2-dimensional and 4 one-dimensional ones. these are the reducibles of the quaternion group. So this is Q subgroup of SU2, and this is a group G into SU3. Yes? And in each of these triangles, you see you have exactly here 9 times 3, you have 27 triangles. So you make a matrix 3 by 9, and you check that those numbers exist, and that tells you that there's a subgroup. So it gives you exactly the information that these are the irreducibles of a... Yes. Exactly. It's exactly, the condition is that those cells exist. So if you find these cells which satisfy those conditions between neighbors, you remember for every pocket you make something like this frame. This could be 2 of these arrows. And then you have the cells, and you take the sum over all the lower things of the product of the W of the triangles, yes? Which means that this matrix is very much in the spirit of what Uffe Horup is going to talk about. It's a Sorin-Popper matrix. It should be bi-unitary, basically. I mean, it should satisfy unitarity condition one way and an isometry condition the other way also. So it's just the fact that up to scaling it's unitary both ways, so isometry both ways. So this is what the cell conditions come. So if you check that, then it's a subgroup. If not, it's not a subgroup of SU3. So it's necessary and sufficient. So it's a local condition of what Sergio Doplicher was talking about. I mean, those big coefficients in this case, because you start from SU3, you have already the structure of SU3. All you need to check is how SU3 acts on this. And that's contained in the cells. So you don't need to compute big 6J symbols. You need to check only these little numbers, these little cells. And there are similar conditions for SU4 and so forth. So you can indeed check the classical case as well. And in the classical case, you'd also get a root system, which is also new. So that one looks a bit more like the affine. I mean, if you start with classical groups, with a classical group, that's the affine form, and you get something closer to the affine roots. If you want to get the usual roots, you have to start from the quantum, from our cutoff thing. Maybe that's why they haven't been observed. This could be another reason, because our objects, I mean our cutoff subgroups, the 6 C8s and so, were not so well known outside the operator algebra.